Solutions to partial differential equations is very important because it has many applications in physics and like elasticity, thermodynamics, hydrodynamics. The partial differential equations has many applications. So the numerical solutions has to be find out in any of these cases. So in order to discuss the numerical solution to partial differential equations, and certain methods are discussed in my seminar topic, and the Laplace equation is the simple derivation of Laplace equation, which is not very much necessary and is given, and we can see that the Laplace equation is a temperature or heat conduction equation, and Laplace equation is given, and the numerical solution of Laplace equation is the main problem. So today we are discussing about the finite difference approximation to derivatives. So in the case of partial differential equations, there consist of two independent variables. Suppose the function we take as u is equal to u of xy, then the u is dependent variable and x and y are independent variable. So in the case of ordinary differential equation, we can write the step size as follows, and it is very easy. And but in partial differential equation, when the two-dimensional representation of and the numerical solution of the partial differential equation is quite difficult. So because the possible partial differential equation arises are ux, uy, uxs, uxy, uyy, etc. As you can see. So we instead of we taking as x is equal to so in finite difference approximation method, we take as the set of lines x is equal to ih and y is equal to jk, and where I and j values varies from 0, 1, 0 to 1, etc. So the figure becomes like this to this. This is the finite difference approximation of partial differential equations or functions with the two independent variables. So it is quite easier to solve this, and we can see that coordinates in the finite difference form. Let u is equal to u of xy. We can the coordinates can be represented as u is equal to x can be replaced by ih, and y can be replaced by jk. The increment of u of x plus h y r, and the solution are u of I plus 1j and u of I minus 1j, u I j plus 1 2 j plus 2, and u of I minus 1j minus 1 are represented. So the representation is quite simpler. So now we have to change the dou square and x square by and dou square y square, dou square by dou y square into ordinary operators by the finite difference approximation method. So in order to that, we apply Taylor series expansion, and Taylor series expansion of ui plus 1j is given, and we put it as equation number 1. Similarly, ui minus 1j also Taylor series expanded. The equation number 1 can be rewritten as follows, rearranged as this follows, and by dividing throughout by h, and we get the equation number 3, which is the solution or finite difference approximation of ux in terms of ui plus 1j minus uij by h, and other terms of other higher order terms of h. OH means other higher order terms of h. So equation number 3, we can see that it is in the form of forward difference approximation, forward difference approximation method, because we studied that forward difference in interpolation, and so it is like a forward difference approximation. So the ux can be said that is the finite forward difference operator for ux. So other terms, the OH can be said that is the error terms in finding ux. Then similarly, ui minus 1j we found in equation number 2 can be easily made to u and easily made in the change to change to ux in another form, and it is in the backward difference operator form. So the equation is represented as equation number 4, and equation number 1 and equation number 2, that is equation number 1 and equation number 2 are subtracted, and we get the another equation which is the central difference operator for ux. And adding equation number 1 and equation number 2, we get the final difference operator for dou square u by dou square. So we can say that the error will be minimum when the central difference operator or ux is equal to ui plus 1j minus ui minus 1j by 2h and other terms of h square is used. By the same method, we can also find uy and in both forward represented as equation number 7, and backward as equation number 8, and central and equation number 9, and uyy as equation number 9. So uyy means dou square u by dou y square. So it is called the finest difference approximation of derivatives. We can simplify it as follows. We here do not consider the error terms. We do not consider error terms. We know that in ordinary differential equation we studied in interpolation, and also the forward, backward, and central. The y dash of x is represented as here, and the forward, backward approximation and central approximation is also here we got in finite. We arrived or we derived in finite difference approximation method, and it is without the error terms are represented, or higher order terms are without a higher order terms are represented. When we consider ux, the j is constant. When we consider uy, the I is constant. So ordinary differential equations and the comparison between the partial differential equation in finite difference form is shown without error terms. So it is called the finite difference approximation to derivatives. Then we go to standard 5-point formula. In order to derive standard 5-point formula, we have to consider an equation. Suppose we consider the Laplace equation. We know that del square u is equal to 0. U may be a function of temperature. Okay. This is Laplace equation. Laplace equation is represented as equation number 11. And we put ux and uyy, that is got from equation 6 and equation 10 to equation 11. Then we get the solution as the standard 5-point formula. We get the 5 points are here. In this formula there are 5 points. So finding the 1 point's temperature, or by the neighboring 4 points, it is called the standard 5-point formula. Thus we got the 4 points, the 4 points temperature, we get the another points temperature. The value of u at any point is the means of its values of 4 neighboring points. So it is called equation number 2 is called standard 5-point formula. So here error terms are not considered. So we have to consider the error terms. When we add equation number 1 and equation number 2, the equation number 1 is this, and equation number 1, 2, and we get equation number 14 and equation number 14, and equation number 14 it is in H type of equation. There is another in K type of equation when we change the J or Y axis in finite difference. So K type of equation we get, and put H is equal to K. Here we have to it is important that H is equal to K is used, because in standard 5-point formula we also neglecting the errors and H is equal to K are put. So the mesh or grid like structure becomes a square structure. h is equal to k and y is equal to k. So the mesh or grid structure become a square structure, and we get equation number 15. The equation number 14 and equation number 15 are added. And we added equation number 14 and equation number 15. Then as you know that ux plus uyy is 0 because it is the Laplace equation. We take it as equation number 11. U plus uyy is equal to 0. So adding equation number 14 and equation number 15, this term becomes 0. This term becomes 0, and we get to the solution as above. And uxx can be represented as uxx of uxx into uxx of uyy minus uy. Because uxx is equal to minus uyy by Laplace equation, so uxx can be changed to minus uyy. So uxx is changed to uxxyy, or uyy is changed to uyy. Similarly, we can change the uyy to uyy. This put it on this equation. Equation 17 is put on the equation 16. So equation 16 becomes like that. The order is not important, so we can add this. We can add this dou square by dou x square plus dou square u by dou y square is 2 times. This term becomes 2 times the dou square x by dou square into dou square u by dou y square. So we get equation number 18. This is the standard 5-point formula with the error terms, the error or higher order terms. When the error terms are not considered, this will become the exact standard 5-point formula, and it is represented as in equation number 12. Now we go into diagonal 5-point formula. Diagonal 5-point formula here. We become the h is equal to k. The mesh or grid structure become x is equal to k, and the diagonal points are considered of uij. Standard 5-point formula only we considering the, suppose this is uij, so we considering in standard 5-point formula ui plus 1j, uij plus 1, ui minus 1j, and uij minus 1. In diagonal 5-point formula, the for diagonals of uij are taken, and h is equal to k. The same procedure in standard 5-point formula, and is taken, and we get a square like or mesh structure, and the x and y axis are rotated to 45 degree. So the distance between the 2 points p uij becomes p. Let's consider this as a variable. It is as p, and by Taylor series expansion, ui plus 1j plus 1 is uij plus p dou u by dou x plus p square by 2 factor dou square u by dou x square p cube by 3 factor dou q by u by dou x cube. The Laplace equation remains invariant when the coordinates x are rotated to 45 degree, and ui minus 1 j minus 1 also Taylor series expanded, and equation number, we get to the equation number 20. Adding equation number 19 and equation number 20, we get uxx as follows. Similarly, changing the uyy also got it. We can put it as equation number 21 and equation number 22. The Laplace equation is uxx plus uyy is equal to 0. So substituting this, we get the diagonal 5-point formula. Okay, diagonal 5-point formula. It is represented as equation number 23. So knowing the 1 point and 4 of its diagonals, we can find the any of the temperature by In the case of Laplace equation, we can find the any of the function u or variable u. Standard 5-point formula with error times also be calculated. It is equation 24 represents the standard 5-point formula of the diagonal 5-point formula of with the error types. It is similar like equation number 18. Equation number 18 is the standard 5-point formula, and equation number 25 is the diagonal 5-point formula. Equation number 24 is the diagonal 5-point formula with the error types. So we know that here h square plus h square is p square. So 2h square is equal to p square, p raised to 4 is equal to 4h raised to 4, p raised to 6 is equal to 2h raised to 6, 2 raised to 8h raised to 6. So the substituting p raised to 4 is equal to 4h raised to 4 in the equation number 24. The 24 equation number becomes the equation number 25. And comparing, now we can compare the standard 5-point formula with errors and diagonal 5-point formula with errors. As you can see, the diagonal 5-point formula with errors, equation number 25 with the standard 5-point formula with errors, equation number 18. It is minus 1 by 6 h raised to 4 ux x y y, and equation number 25 is minus 4 by 6 h raised to 4 ux x y y. So it is quite 4 times the error in the diagonal 5-point formula is 4 times the error in the standard 5-point formula. So solution of Laplace equation is quite simply found by this type of method, and this is by considering a boundary region R with a boundary C, and that the value of u is specified everywhere in the C. So the rectangle, or sorry, the square-like structure of the region of is given, and the C values are specified. The boundary values, C are the boundary values, C1, C2, C3 are the boundary are specified, and we can get the interior points. We have to get the interior points such as u1, u2, u3, u4, u5, u6, u7, u8, u9. So we know that standard 5-point formula and diagonal 5-point formula without errors. So apply on this, and we get the u1, u2, u3, u5, u7, u9, and by diagonal 5-point formula and standard 5-point formula we get u8, u4, u6, u2. Thus we get applying this. Suppose we consider u5. This is u5. U5 is the we can see the C1, the diagonal 5-point formula. The diagonal u5 goes to C1. u5 is equal to 1 by 4 C1, and C plus C5, and here it goes to C9, and here it goes to C13. So yes, so u5 is equal to 1 by 4 C1 plus C5 plus C9 plus C13, and u8 and standard 5-point formula u8 can be found by C11 and u7, u8, u5 1 by 4 u5 plus u7 plus u9 plus C11. So thus we can find the all points in the merge points. The iteration methods like Jacobi method, Gauss-Seidel method, SOR method improves the accuracy of the finding the solution of Laplace equation or the diagonal 5-point formula, etc. The first one is the iterative method is Jacobi method. The Jacobi method is is the iterative change of standard 5-point formula to an iterative 5-point formula, and it is also called a point Jacobi method, and uij of n is denoted as n the iterative of uij. So it is represented as equation number 27. Each values of n the iterative points gives another fifth point with the n plus 1 iterative point. So thus we can find the interior mesh points. Gauss-Seidel method is, or another term is Lehmann's method, is more accurate or latest. It includes more latest iterative values in the mesh points. So in the standard 5-point formula, we also takes the n plus 1 and n values, n the iterative values to get the n plus 1 interior mesh point value. So it is more accurate. The more accurate method is successive over relaxation method, or simply called the SR method. And in order to get that method, we equation number 28, which is Gauss-Seidel method, it is modified into like this, and one the term in the bracket 1 by 4 ui minus 1 j n plus 1 ui plus 1 j of n ui j plus 1 of n ui j minus 1 n plus 1 minus 4 ui j becomes 1 by 4 rij. So Gauss-Seidel iteration method, the 1 by 4 rij is the change of uij is changed to uij of n plus 1. So uij of n means the n the iterative value of uij, and uij of n plus 1 means the n plus 1 iterative value of uij. So the change to one iterative value to the other iterative value is 1 by 4 rij in Gauss-Seidel method. So by increasing the change, by increasing the change, we can increase the accuracy or convergence. So we put omega in the equation. So equation omega is put and the equation can be changed like this, and we get the equation number. After deriving, we get the equation number 29, and uij of n plus 1 is equal to omega into uij of n plus 1 minus omega uij. Here we get the omega can be called as an accelerating factor, because it depends, omega depends the convergence, and it becomes the value of 1, and its values lies between 1 and 2. As we can know, the percentage error in uij is given by uij, the uij of n plus 1 minus uij by uij of n plus 1, the modulus into 100. It gives the percentage value. We have carry shown that the omega is equal to 1.875. The rate of convergence of equation number 29 becomes fast as that twice as fast as that omega is equal to 1. So for omega is equal to 1.9, the rate of convergence is 40 times greater than that of when omega is equal to 1. In general, however, it is difficult to estimate the best value of omega. So it is simply is that in SOR method, omega determines the convergence. So oscillating factor is is very important in SOR method. So that's all. Thank you. So we can discuss some more problems about the finite difference approximation methods and the solution of Laplace equation regarding this topic. For this we have to know the standard 5-point formula and diagonal 5-point formula and the Jacobi's point formula. Both are given above, and the problem is the solve the Laplace equation for a square region, which is given as there. And we know that because the standard 5-point formula, you can apply it. U1 is equal to 1 by 4 into 2 plus 4 plus U2 plus U3, and U4 is equal to 2 plus 4 plus U2 plus U3. Or there is another method for finding which is very simple. That is when we consider A to C as a diagonal, there we can see the symmetry 1 1 2 2 4 4 and 5 5. So there is a symmetry there, the values on the boundary values being indicated. So we can simply say that u1 is equal to u4 according to symmetry, or by simply applying the standard 5-point formula. And the standard 5-point formula can be replaced as, and u1 is equal to 1 by 4 into u1 plus u3 plus 6, and the simply putting iteration formula, which is the Jacobi's method, and iteration formula, the iteration formula becomes 1 by 4 u1 of n u3 of n plus 6, and the there we another approximation, since u2 is close to 5, so we can simply say u2 of 0, which is u2 of 0 is becomes 5, and u2 u3 becomes close to 1. You can see the u3 is close to 1, so u3 of 0 becomes 1, and simply putting on the equation u1 of n plus 1 by 1 by 4 of u1 of n u3 of n plus 6, we get the equation u1 of 1, the first iteration value of u1 of n becomes 3, and the second iteration value of u2 of 1 becomes 4. So the u3 of 1 becomes similarly the iteration formula for the points q and r are given as this type, and thus we can find the second iteration and values. So we can find u1, u2 and u3, u4, etc. Another example is solve the Laplace equation by Jacobi method and Gauss-Seidel method, and so on. To start Jacobi's approximation method, and the values of u1, u2, u3 and u4 by Jacobi's iteration method are found. That is because u1 is equal to 0 plus 0 plus 0 plus 1, and u2 is equal to 0 plus 0 plus 0 plus 1 by 4 times. So the the values are found, and we iterated, and we get the values as like this. And Gauss-Seidel method, we apply Gauss-Seidel method, and we get the iteration values as there, and putting omega is equal to 1.1, the successive iteration method, successive iterates, and we get the u1, u2, u3, u4 values are given.